All right, everybody. Thanks for attending the session. Little background on myself. I am currently a Juniper architect. And prior to this, like many of the people in the audience, I started my career off at a university, Northwestern University in Illinois, where I used technologies such as MPLS and layer 3 VPNs to virtualize the network. So I'd like to start off by raise of hands. How many here have a campus network? All right, that's just a handful. And then though you may consider your organization to be a service provider, a co-location facility, cloud provider, hyperscale, you still have departments such as sales, engineering, finance that essentially connect to a campus LAN type network. Point being, every organization in some form or fashion is a service provider and runs a campus network. You have these users, again, engineering, legal, finance. They connect to the campus network, and you're giving them services such as DHCP, DNS, NTP, maybe authentication services. One more question before getting into the meat of this. What's the first thing that you think about when you hear EVPN? Data center, right? What I'd like to do over the next half hour is to talk about EVPN for everyone else. I'll recap how networks were built for the campus, why they were built that way, as well as some of the issues. How campuses and data centers differ, why EVPN makes sense in a campus, and then how can you enable and migrate to an EVPN-based core. And even if the campus, stick around. This architecture can be used in many other scenarios. Here, we see a typical circa's 90s three-tier architecture, the classic core distribution line. How many of you have either supported, designed, deployed, or recommended this architecture in their careers? I'm sure, there you go. Would you still do that today? Maybe. And there's nothing wrong with this architecture. At the time, devices have cam. There was a clear distinction what a router was and what a switch was. Devices such as bridge routers or layer 3 switches were still just coming online. This architecture was in the ICND book, Interconnecting Network Devices, the CCNA book. It was in SNR. I mean, I've visited places where that campus network's IP addressing came straight out of those books. Through the years, there have been slight variations, maybe combining the core and the distribution layer together as hardware became more capable. So throughout this core distribution, that can be used interchangeably. Many of these environments are looking to refresh. They need a refresh. They have older CATs, Brocade, Juniper gear. My hope here is when you go and look to replace these core devices, we don't go out and just ask the manufacturer what the latest greatest is and do a one-to-one box swap just for the greater speeds and feeds. I challenge you to go and rethink the campus going forward. So here is a typical campus. We have 2 data centers, maybe the headquarters with a core of their own, with multiple distribution switches, maybe a small office with a switch per building. Again, we've all seen it before. All valid campus deployments. What are some of them? Redundancy, spanning tree, flooding and learning, our users, layer 2 adjacency, as well as segmentation. And I'm going to go deep into these a little bit more. Redundancy. Adding or redundant paths in case of a fiber cut or equipment issue is always a good idea in a switching environment. But we all know that causes loops. And when we get loops, we need things like spanning tree or similar, When the campus was small, a couple hundred or 1,000 devices at work, not that big of a deal. But with laptops, IP phones, and that's just the users. How about building automation? HVAC controls, IP surveillance, IoT. The consumers of these networks have grown exponentially and evolved, but has the network? Anyone here ever experienced a core meltdown? You walk into the switch room and all the blinky lights, all the LEDs are flashing at the same time, and then you're struggling to find out and turn off ports to find out where that loop is? It's never a fun time. Let's recap how spanning tree works. Right? There's an algorithm that essentially determines loops. Then we figure things out like the root port, the forwarding port, they're determined, as well as the blocking port. So blocking, that means that I don't get all my available bandwidth. We shut off to prevent loops. So here's a little test. Given this simple topology, which ports are blocking? Anyone? All right. What info do you need? Now, is it clear which port's blocking? Still no, huh? All right. Given that, we should be able to determine it, right? All right. Test is over. There we go with the blocking ports. So my point being, in this small node 4-switch environment, we can figure these out. We can turn knobs to essentially determine and force which port is blocking. But imagine a network, a campus network, with hundreds or thousands of switches. Again, when things were small, it's a lot more manageable. As an industry, we've also tried to get rid of spanning tree while maintaining this redundancy. We've created technologies to make multiple devices appear and act as a single device. We have virtual chassis or stacking. We've created virtual chassis fabric, multi-chassis lag, Juno's Fusion, or Cisco's Fabric Extender. All of these devices were created to act as a single logical device. But the moment you connect one of these devices or logical device to anything else, we need to reintroduce spanning tree. And now we're back learning. ARPs and GARPs, ask everyone who someone is, or tell everyone who I am. We flood that MAC address across the entire broadcast domain. And all of these technologies have worked to some degree and helped mitigate the need for spanning tree, especially when you carefully do all the calculations. But here's the problem. There is no interop between vendors in any of these technologies. It's rigid. Each vendor, while similar in concept, has their own specific implementation. We all love our users, right? The unique and interesting challenges they ask of the network. Layer 2 adjacency. A lot of legacy apps are dumb or programmed at a time when there was a single network. They used flooding to exchange data, or maybe local multicast, which necessitated to be part of the same layer 2 domain. All good when everyone is on the same switch. But let's take the following scenario. A professor or a student, maybe a VP in engineering, or identity-based firewalls. We put users into different VLANs or subnets based upon the floor of the building that they were in or the functional group that they were in. And at the time, it made sense. You know, we had a specific IP subnet assigned to them. How about, or they get that new corner office on that 35th floor, the tenured professor who has 2 different offices? What were the options when we created firewall rules based upon these subnets when the professor moved from one place to another? Did we just create a new firewall rule and make switch? No. Collectively, what we've done is put that port where that user is on that same VLAN, and we stretch that VLAN across the core, crossing multiple routers, multiple switches. And that would be fine if it were just one. but it never was. Segmentation. At some point, we figured out it was a bad idea to put everyone in the same /16 broadcast domain, all in the same VLAN. We saw things having these huge broadcast domains and flooding wasn't a good idea, so we segmented it even further. We went to /, with the help of VLSM. As we saw in the previous slide, historically we grouped users into logical functional groups and then put members of these groups into subnets, specific VLANs, to help segment one type of user from another, to provide security. The fault here is that IP reachability to any other group, unless you put in complex ACLs or firewalls in between every subnet. I know that there are many other challenges in a campus environment, but these are just the main ones I wanted to bring up: redundancy and users. Let's chat about the data center versus the campus. Quite a few data centers are moving to a spine and leaf with an underlay and an overlay. There must be some reason. Standards-based, leverages BGP and BGP to be precise. EVPN for control and the data plane for layer 2. We still flood at the edge, but then use BGP to exchange MAC addresses with other devices. But why are they doing this? What types of problems are they trying to solve in the data center? Layer 2 adjacency. They too have legacy apps, maybe not the hyperscale guys, but everyone else. VLAN limitations. VLANs can only scale to 4K. Microsegmentation, getting rid of spanning tree, any port on any VLAN anywhere. Now, if we look at the picture, the data core are not too different. There's a similar set of challenges. In the data center, we have spines. In the campus, we have core and distribution boxes. There are leaves, and then there's access switches. So with these similar set of challenges, VLANs, getting rid of spanning tree, limiting of flooding and learning, as well as the flexibility users require, why don't we leverage EVPN in the campus? Here we see what a full fabric looks like. EVPN VXLAN, it's on the core, as well as the spines, as well as the leaves, maybe even across the WAN. We have lean spine, where the spines are just doing routing and nothing else. The EVPN VXLAN domain only exists at the access. And finally, spine only, where it's the opposite, an EVPN VXLAN only in the core, and then only layer 2 at the access. Again, with so many similarities, why not leverage EVPN in the campus? Why not leverage all the benefits that EVPN, again, standards-based, large industry adoption of EVPN, minimized fault domain. If I lose a core box, am I down? Worst case, 50% capacity. And it's easy to scale. If I need to add 40, 100, 400 gig, I'm not locked into specific boxes or even vendors. All of the same advantages a fabric has in the DC. But here's the difference and the key with ECC architecture. You do not need the access boxes to speak BGP, VXLAN, or even EVPN. Let me repeat that. No BGP, VXLAN, or EVPN at the access. And that's the beauty of a Vault Campus core. We use a spine-only model where EVPN VXLAN resides only in that core distribution layer, nothing at that access. The feature that ties everything together here for the campus is called ESI lag. And I'll talk about that in detail in a few slides. But for now, just think about standards-based mechanism for MC lag. This is also perfect for brownfield, unless you're lucky enough to build out an entirely net new campus. Operationally, nothing changes at the access layer. All the knowledge, the skill sets, NOC and operations staff doesn't change at all. Configuration, troubleshooting, or any automation that's been built for the access doesn't change. All that stays the same. Let me repeat that. Nothing changes at the access. And that's huge, which is usually a barrier for entry for most organizations. Now that hopefully I've convinced you why EVPN in the core of a campus makes sense, let's get into some details. Here are the 5 key concepts of ECC: Underlay, Overlay, EVPN via Segmentation, ESI lag, and Anycast Gateway. These are the 5 key concepts that I want to make sure everyone in the audience today understands about ECC architecture. Start with the underlay. Similar to what we've seen in the compute virtualization, what we do there, we do with the network. On the compute side, we've started to build in a massive bank of general computing power, and that's what we do with the underlay. We just build out a big amount of non-blocking IP connectivity. And for that, you can use BGPs. All that's really needed is loopback reachability between these EVPN cores. Overlay, sticking with the compute virtualization, not too interesting when you have some compute with nothing running on it, instead of taking over and running 1 or 2 apps. We said, hey, let's get more efficient and leverage everything that we can out of this compute, be it efficiency, costs, sharing compute cycles. That's where the hypervisor comes in for compute, right? Allowing us to run VMs of physical machines like web, app, DB on that general bank of computing nodes. Akin to the network, why would we build out separate physical networks for engineering, legal, or finance? We should be able to run them all on the same network platform. VRF segmentation. We've made VMs as an hardware, just like VLANs to segment one user class from another. But how about if I wanted to have the ability to create VMs of web app DB, but then we can group those VMs together as dev, test, and prod? Every environment can have identical systems, but never talk to each other unless we explicitly allow them to. So how about if we take engineering, legal, and finance, and not only did we segment them by VLANs, but we created their own isolated network. So engineering here talk to finance if they're all isolated from each other. We would put a firewall here that's connected to each VRF, which can then route and firewall between all of them. And you get the following 3 benefits here. Without segmentation, everything is in the same routing table. There's neat rule sets, some combination of allow from here, deny from there, and depending upon what the subnet is. Again, very complex. Second, there is an air gap between segments. The only point that these segments cross is at the firewall. The third point, as a result, these rules become very clean, simple, and portable. Similar functional networks are then grouped together so that the point of view of that VRF or overlay network is truly inside and outside or the internet. ESI lag, EVPN multi-homing. Everyone here has heard of VPC or multi-chassis lag. Take 2 unique devices, 2 unique control planes, and make a downstream device. Think that I am a single entity. Has anyone here tried to make one chassis, an Arista, and another Juniper as part of an MLAG? Why would you? You couldn't, right? 2 of the major advantages of ESI lag is the ability to scale past 2 devices to 4 or even higher, as well as being standards-based. ESI lag is a state of multi-chassis lag. Now, ESI lag is a bit of a different concept, so let's dive in a little bit more. All ESI configuration happens at the core distribution layer. Again, nothing special at the access. From the access point of view, it's just the normal AE interface, port channel lag. Think of these as unidirectional lags. From the access, it just sees a lag interface going up. Doesn't matter which core it hits to get the traffic out. but from the core distribution, a lag interface, and we assign it an ESI number. So in this example, for the left switch, we create an ESI ending in 01, middle switch 02, the one on the right, 03. And what we do here is we have to create a global unique ESI number, but make it the same for that specific access layer switch. So if we take this example, there is a ESI to MAC mapping. And that was populated on that host ending in B7, 6B, initially sent traffic. It populated the one core device. And now via an EVPN route update, populates the other core device. So when traffic comes back on the way in, it'll look at that mapping. It'll say B7, 6B, that's mapped to 002. Send it down to that switch. And if it happened to hit the other core, same thing. It has that same table down to the right switch. And that, in a nutshell, is ESI lag. Anycast Gateway. Your HRSRP works well, but only in the active. One is active at any given time. So really, you only have 50% usable bandwidth. In ECC, every gateway is active, hence the term Anycast Gateway. Oh, and not only all are the devices active, just like ESI lag, you can scale core distribution devices. In a failure with VRP, the other devices taking over routing, depending upon what caused the failure and if there was a spanning tree event, could take a while. And when that loses, you're taking time to recover. In any cast scenario, especially if you have 4 boxes, the probability of you hitting that box is much lower, and as a result, your fault domain is minimized. So we talked about the why and at a high level, the fundamental pieces, but the next question is how? We start with the physical topology. Remember that 3-tier architecture? If we look at ECC and the physical topology, it's similar, if not identical. Chances are the campus network is already laid out that way. This is how we built networks for access layer redundancy. So we didn't do everything wrong due to fiber or other limitations. And that's OK. It doesn't mean that you can't move to an ECC architecture. You just won't be able to reap the benefits of things like ESI lag or Anycast gateways per se. Once we figured out the physical, hardware and software, the architecture is called Evolve. ECC revolves around the core distribution layer. Update the core distribution devices. Make sure they are capable of EVPN VXLAN. You may already have devices capable. It might just require a firmware upgrade. Again, at the axis, nothing has to change. You don't have to touch the axis as long as it supports TCP and VLANs. And finally, the last step to enable ECC on those devices, the underlay, the overlay, VRF segmentation, ESI lag, and Anycast Gateway, all of which were only configured on the core distribution devices. And I've only been showing, but you bring back the multi-site campus, and when you start to configure ECC, you'll be able to satisfy the redundancy and user problems that we talked about at the beginning. Once you start configuring all these kind of pair of nodes together, you can start with one in the corner, and then as time permits, start doing it all around the campus, and you will enable EVPN VXLAN in your core. A question, why spine only? And here's the reasoning. It's probably going to be easier to upgrade a handful of core devices as opposed to 100 or thousands of access layer switches. Again, nothing operationally changes at the edge. The support staff have time to ease into EVPN VXLAN. Also, today for the campus, EVPN VXLAN is capable multi-gig PoE++ type switch at an affordable cost. I know they're just coming out on the market, but point stated. Once you get the core set and time moves on, you can then migrate to a full fabric when those access switches become readily available, push them down. So you can go to either the full fabric or the lean spine. But starting with spine only gives you many options. So in summary, the takeaways: why ECC? Redundancy, users. Underlay, overlay using EVPN VXLAN, VRF segmentation, ESI lag, and Anycast Gateway. And finally, the migration. 3 steps: physical, EVPN VXLAN, core upgrades, and then enabling ECC. I think we have a couple minutes for questions.
Hi, Jay Kuhn, Semantics. You talked a lot about the campus network connectivity intra-campus, but
As long as there's IP reachability, and take it with real-world testing, as long as there's IP reachability, you can extend that layer 2 between any points as long as there's the IP reachability between loopbacks. It's essentially a BGP peering relationship between any of those nodes. But that doesn't mean that you can't use it as a transit provider or even in a hosting colo scenario. So just look at that and apply it to your own environment. Thank you.